So let's talk a bit about absorption now. Don't forget, emission is when electrons go down from their higher states, releasing a photon of that energy difference. Okay? So absorption is the opposite of that. We're going to try and knock electrons to higher states there so it absorbs energy. So if you were to shoot electrons through here with any energy above 10.2, let's say we gave it 11, it is possible for this electron to collide with an electron here and actually raise it to a higher state, and this would be left with maybe 0.8 here left over, wouldn't it? So to lose its 10.2 for this electron and be scattered with 0.8. So it could do that if it's an electron. Okay? So electrons with at least 10.2 should start to excite atoms in this gas. Photons cannot do it that way. If photons come through here and they have a value of 11 electron volts, they will not cause this to go to higher state. Why is that? So if you look at it here, a photon needs to lose all of its energy or none. So, can it lose all of its energy? No, it can't, because that would cause the electron to go from here to that position there, which it cannot do because that is not a stable position. It cannot absorb 11 electron volts. So photons coming through here with 11 would not be absorbed. The only ones that could be absorbed then, if you look at it, are the photons that have exactly energies of this much. 10.2, that would be absorbed. 12.09, that could be absorbed, and so on. So the only photons that can be absorbed by this particular gas, hydrogen, is the ones that actually match those 10.2, 12.09s, and anything in between would go straight through. And that's why you get line absorption. So line absorption occurs when you get a white light source or a continuous source of white light, and you've got all the colours going through, and it goes through a cooler gas, which is an elemental gas, a gas made of one element maybe, or several elements. And then you look at it through a spectroscope or a diffraction grating. In this case, most of the photons of light go through quite happily, but what happens with some of them is they correspond to these energy jumps going up, these 10.2 and the 12.09. So in that case there, those are absorbed and then re-emitted in several directions. Okay? So there's a significant drop in their intensity for those particular frequencies or those energies, and that's why you're going to get these blacker lines here appearing just there, because those frequencies have been absorbed and then actually re-emitted in all directions by the atoms in that gas there, and that's why you get line absorption. And that's actually the, I guess, the negative image to the line emission series you get from hydrogen here. Okay, so line absorption is caused by just the right photons being absorbed that match the jumps going up, scattering in all directions, and then you get a loss in the intensity there. And you can sort of see here that the line emission then is kind of mirrored here compared to the line absorption there. At room temperature then, if you tried to do this with, say, a white incandescent lamp, pass those through the cooler gas there, you would only find the ones that are actually absorbed are in the ultraviolet region, because this is the UV region. So you wouldn't be able to see that then. Okay? The only way you can see visible lines there in the line absorption region was if you actually somehow managed to get the hydrogen in between you and the white lamp to be sitting in that state. And the best way of doing that, of course, is to heat it up, actually warm it to a higher temperature, so that some of the atoms are knocked to this higher state for a brief period of time, and then they could absorb some of those photons and cause some line absorption in the visible region, which is what we want. But normally you can't see them. It's possible, of course, it's typical for stars to produce incandescent light or a whole range of frequencies, and then as it goes through the cooler outer layers of the gas of that star, those elements there will absorb certain photons and re-emit them in all directions and give you those black absorption lines characteristic to that element. And so if you look at line absorption for certain stars, you can tell which gases are in their cooler outer region, okay, and identify what's going on with the star. Right, so the last thing I want to discuss here with this atom idea, just briefly, is fluorescence. So fluorescence is when you get certain materials that absorb ultraviolet light and raise to higher states. Okay, so they'll absorb an ultraviolet photon of high energy, go to a higher state, and then they'll return to ground state in a series of smaller jumps like this, releasing photons of a lower energy. So you're going to take in a high energy photon and convert that to lots of smaller energy photons in the visible region. Okay? And that's called fluorescence, because all of a sudden you've taken UV light, which is invisible, and you convert it into visible light, and so you see those things glowing. You might suddenly see people with white clothing when they step into a black light or an ultraviolet light, and it glows very bright, those white things do. So that's the process we're talking about. So having been raised to a higher state, those particular materials return back to a lower state by a series of smaller jumps like this and release lower energies in the visible region, so you get that glowing effect. Okay, thank you.